right, so the next question is circular permutation and binary representation. Just give me a moment to make sure the audio is working. All right, so the next question is, nice. Okay, circular permutation and binary representation. Let's give that a shot. See how this goes. So give that a new thing here. Circular permutation and binary representation. Given two integers and in start, your task is to return any permutation p of 0 to 2 to the n minus 1, such that p of 0 is start, p of I is equal to p of I plus 1 differ by only one bit in their binary representation. P of 0 equals p 2 to the n minus 1 must also differ by only one bit in their binary representation. Okay. Really low submission rate, kind of a high acceptance rate. Some upvotes and downvotes. Kind of, I don't know what to make of this one. So n is 2, start is 3. Excuse me, output 3201. Binary representation of the permutation is 3201. All the adjacent elements differ by one bit. Another valid permutation is 3102. So n equals 3, start is 2. Binary representation of the permutation is 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1. This is like a gray code type of a thing. Any permutation p of 0 to 2 to the n minus 1, such that p of 0 is start, p of I and p of I plus 1 differ by only one bit in their binary representation. P of 0 and p 2 raised to the n minus 1 must also differ by only one bit in their binary representation. So this is kind of like a Tor. N can be 1 to 16, and 0 is less than or equal to start is less than 2 to the n. So I have to visit every number, right? If n is 16, 2 to the 16th is like 30,000, something like that. 2 to the 10th is like 1,000. 2 to the 6th is like, I think it's like 65,000, something like that. Yeah, 2 to the, it's 8 squared. That's like maybe 65,000, something like that. So I think this is technically a Hamiltonian cycle, I think it's called, through the graph. So an Euler Tor visits every edge. Hold on, Euler Tor wiki, right? Eulerian path, and then a Hamiltonian Tor, Hamiltonian path. Hold on a second. Sorry about that. Okay, so back to what we're doing. This is, oh, gee. It's only been a few minutes. Sorry about that. Sorry about interrupted. So the issue that I've run into, is this, yeah, audio is fine. I take a deep breath. With great difficulty. Now, okay, so Eulerian path in graph theory, an Eulerian trail or Eulerian path is a trail in a finite graph that visits every edge exactly once, allowing for revisiting vertices. Okay, so every edge exactly once, a little bit different than Hamiltonian, which visits every vertex exactly once, right? So starts and ends at adjacent vertices can be completed by adding one more edge to form a Hamiltonian cycle. So we're looking for a Hamiltonian path, right? That's what's being asked for. And the edges in the graph are going to be basically the bit representations, right? So each vertex is a bit representation, and then a difference of 1 bit, either flipping a bit to 0 or flipping a bit to a 1 is what's being asked for here, called for. So yeah, I mean, this is interesting. So the thing about Euler paths and Hamiltonian paths is that they are in general, so I think, what is it? Eulerian trails and circuits, Herholtz's algorithm could be done, I think, in linear time, right? Yeah, this is kind of an interesting question or solution. There's this, you can calculate how many there are. Yeah. Interesting. Product of a certain degree factorials and the number of aberracences, which can be calculated using the matrix tree theorem. Anyway, Veblen's theorem. Sorry, forgive me. I have so many things on my mind to think about. It's hard to focus. Give me 1 second. Actually, speaking of which, hold on a second. Anyway, yeah, I gotta keep my door closed. All right, so Hamiltonian path, undirected. Yeah. So Hamiltonian paths, unlike Eulerian paths, right? So there's apparently a Herholzer algorithm that you can use, which comes from a very long time ago, 1873. This has been known for 150 years now, that you can do calculate Eulerian paths in time that's linear. Pretty cool. I have to like implement this at some point, and remember it, because it comes up from time to time. But anyway, so Hamiltonian paths, on the other hand, I think are NP complete. or NP hard, NP complete or NP hard. I think NP complete if it has a cycle. Yeah, NP complete. Yeah. However, this particular this particular setup, I think, is not NP. Like, I don't think it's that hard to calculate. Well, even if it is, actually, if it takes exponential time, no, the number of vertices is no, you can't. Yeah, okay. The number of vertices here is actually 2 raised to the 16th in the worst case. So if I have an exponential time algorithm, it's gonna take too long. Yeah. So I think there's a way to do this though that's efficient. In other words, I don't think this particular instance of a Hamiltonian path is too hard to calculate. But I'm not doing myself any favors by converting this to a graph question. Many questions can be converted to graph questions, and it's easier to work on that graph question. This would be, in general, actually a harder conversion if I were to do that. This would, basically, I should look at this as a special case of a Hamiltonian path that's easier to. Oh, here we go. No, it's not. It's not necessarily connected. I think it might be planar though. This. I think you could prove that this graph would be planar. This one. Maybe I'm wrong about that. I don't know. A simple graph with n vertices has a Hamiltonian path if, for every non-adjacent vertex pairs, the sum of their degrees and their shortest path length is greater than n. Oh. Interesting. Graph is Hamiltonian if and only if its closure is Hamiltonian. Interesting. There's quite a few different theorems that they've come up with. Properties. Rotation graph is Hamiltonian. So obviously, complete graph with more than 2 vertices is Hamiltonian. Obviously, this has to be Hamiltonian, this graph, otherwise you wouldn't be able to do this, right? So it is Hamiltonian, and then the question is, find one such Hamiltonian path. I think I could use I've seen something like this in the past. This is one of those really tricky questions that, the reason it has such a low submission rate is because it's hard to like think through how to do this exactly. I've done something similar to this before. It's one of those very tricky things where if you know it's possible, then you can brute force it. That's what it comes down to. So you actually don't try to do this in a clever way. You do this using a brute force solution, basically a backtracking algorithm. And because it's guaranteed that there's a solution, the backtracking algorithm should be able to find the solution relatively efficiently. That's how you solve this. I've solved questions like this in the past, and every time it's like, wait, what? And it's actually very easy in that sense. And we had a question like that recently too, where it was like, oh, if you just brute force this, it's sufficient. You just have to know that the brute force will be efficient enough for given the constraints. And yeah, like exhaustive search. Basically, just you use a form of exhaustive search, like a backtracking algorithm works fine. Yeah. So okay, just backtrack. And it'll look like the following. standard vector of int results, a DFS int position, and we'll start here. And then return the result. Result.reserve. The size is n, right? That's how many elements. And so what I'm going to do is also have a Boolean. And this is going to be visited. This doesn't need to be, this could be an array, standard array. Standard array of size 1 and false, oh no, yeah, booleans of size 1, I don't know, boolean 1 n. There we go. And this is all going to be filled. Just to say n, or just lmn. Let's do size. That's better. Size. Size result reserve. Also size, and then do a fill. vd plus size. False. And then start with, so if vd of position, then return, come back to that in a moment, vd of position equals true. vd of position is then false afterwards. I'm going to do a loop for each bit. So what I'm going to do is result.pushback and then result.popback. Yeah, that's the idea. So something like the following. Right, it's going to modify the state as I go, and then I'm going to say, so if the size if that's greater than or equal to size, then we're going to return true. Return false. Don't really have to return, we just return. I don't know if I need to show return or true or false or anything like that. I could just do return. And this is going to be for each bit. So int I is 0, I is, or bit is 1. There are, actually it's just going to be flip the bits, right? Differing by 1 bit means it just flip the bit. So it could be, starting position, n is the number of bits, right? Yeah, n is the number of bits. So if n is 0, 2 to the 0 minus 1 is, n is not going to be 0, but n is 1. You get 0 to 1. Yeah, it's just one bit, right? Okay, that's number of bits. So I is less than n, bit shifts by 1, I increments by 1. Each bit, we're going to say const int next position. That's going to be this position XORed with the bit. So if there's a 0 there, it becomes a 1. If there's a 1 there, it becomes a 0. Yeah. And this next position we're going to call f of next position f. Yes. Something like this. And at the end of this, I should terminate early. So yes, so return false, return true. Just say if this is true, return true. And at the end of it, return false. That'll allow me to terminate early. That's kind of what I was looking for before. Something like this, I think, does the trick. Just oh, okay. Does it have to be a const expression? I can't do, okay. I guess standard arrays, I can't do it that way. All right, yep, that works. So let's try a few other cases. So it's 16 to, whatever, let's do 16. 16 to some random number. And then similarly, you make this like 60,000. Let's do 1,000, 10,000. Let's do like 8 and 20. And then let's do like 4 and 4, right? Try a bunch of different things. Now normally, yeah, see, pretty quick. So normally the concern would be that, whoa, 64 milliseconds. The concern would be normally that, hey, like it's a brute force backtracking algorithm. It shouldn't be that efficient, right? But because you know it's guaranteed that there's a solution, it actually can find the solution very efficiently. So I'm going to go for it, I think. I'm going to go for it. Could be wrong. Could be missing something important. Nope, got it. Yep, see that. It's not the fastest solution, it seems, but it works. It works. Other people maybe came up with something a little more clever. That's reasonable. Gee, why why 1, 2, 3, 4? Why is it so slow? Should be. It's like not that fast. It's pretty fast to program. It's a pretty quick solution, quick answer, and it's quick to program, and it's almost guaranteed to be efficient. I'm a little disappointed it's not the fastest. Yeah, very few people submitted for this question. This was it's got a lot of people. Look at this. Only like a handful of people on the whole website even attempted this one. Yeah, well, it's a Hamiltonian path, but like I said, if it's guaranteed that there's a solution, then you can find it quickly with the brute force search. I don't know. Yeah, it's not. I wish it was faster. Kind of disappointed it's not as fast as it could be, but that's okay. That's okay. Maybe I can use a something that's not iterative, or something that's iterative that might be faster if I remove the stack and use. If I were to use like I don't know, it's kind of hard actually. If I could use a stack and do this iteratively, but I think it's sort of harder to do that, I think. That might be faster. That might be why these other solutions are a little bit faster. Yeah, okay. Okay. Let's see. Let's go for one more. Very good. Very good. All right. So yeah, I'm gonna stop there. Thank you for watching. I'm not gonna. I could look at the solutions, but I'm not going to. It's fine. I'm just gonna keep going. Thank you for watching. If you like the video, give it a like and subscribe for more. I am going to, I think, take a break.